Assalamu alaikum, brothers and sisters. Welcome to the journey of Quest, where we quench your thirst of knowledge. Did you know that bananas are slightly radioactive due to the presence of potassium-40, a natural isotope? It's a fun fact that opens the door to the fascinating world of isotopes, particularly the radioactive ones. Let's dive into what isotopes are and why they matter. Every element on the periodic table has isotopes, which are versions of the element with the same number of protons, but different numbers of neutrons. This variation in neutron number can make some isotopes stable and others radioactive. Radioactive isotopes, unlike their stable cousins, have nuclei that are a bit too packed or imbalanced. This instability makes them decay, emitting radiation in the process. It's this decay that tags an isotope as radioactive and gives it unique properties and various applications in our world. From the bananas in your fruit bowl to the complex processes that power stars, isotopes play a pivotal role. This natural phenomenon of radioactivity is not just a quirky fact about your breakfast fruit, it's a gateway to understanding the incredible world of radioactive isotopes. Every radioactive isotope has a built-in clock, known as its half-life. Imagine an ice cube sitting on a table under the sun, slowly melting away. Similarly, radioactive isotopes decay over time, transforming into different, more stable elements. The half-life of an isotope is the time it takes for half of the original material to decay. This isn't a process that can be rushed or delayed, it's as constant as the ticking of a clock. Let's take carbon-14 for example. It has a half-life of about 5,700 years. If you start with a pound of carbon-14, in 5,700 years, you'll only have half a pound left. Another 5,700 years later, you'd have a quarter pound. This predictable pattern continues until the isotope is completely decayed. This decay process is not just a curious phenomenon, it has practical applications. For instance, by measuring how much carbon-14 remains in the remains of an ancient fire pit, archaeologists can determine when the fire was burning. It's like a timestamp that nature has left behind, allowing us to read the past. Similarly, geologists use isotopes with longer half-lives like uranium-238 to date rocks and understand the age of the Earth itself. These isotopes act as timekeepers over geological epochs, marking the passage of millions of years. Thus, through their predictable decay, these isotopes help scientists date archaeological finds and understand geological timescales. Imagine a world where doctors can see inside your body without a single incision. This isn't a glimpse into a distant future or science fiction. It's a reality made possible today by the remarkable use of radioactive isotopes in healthcare. At the heart of this medical revolution is technetium-99m, the most widely used isotope in diagnostic imaging. Derived from molybdenum-99 through a radioactive decay process, technetium-99m has become indispensable in hospitals around the globe. Its ability to emit gamma rays, which can be detected by special cameras, allows physicians to obtain clear images of internal organs and structures. The magic of technetium-99m lies in its short half-life, about 6 hours, which is long enough to conduct detailed diagnostic tests, yet short enough to minimize radiation exposure to patients. This balancing act ensures patient safety while providing critical insights into the body's inner workings. Medical professionals employ this isotope in over 30 million procedures annually, ranging from detecting bone metastases in cancer patients to assessing heart muscle activity. By injecting small amounts of technetium-99m into the bloodstream, doctors can track its journey through the body and capture real-time images of blood flow and organ function. This method is crucial not only for diagnosis but also for monitoring the effectiveness of treatment, providing a dynamic view of patient health. Expanding beyond technetium-99m, other isotopes like iodine-131 have transformative roles, particularly in treating thyroid cancer. By targeting cancerous cells selectively, iodine-131 delivers therapeutic radiation directly to the tumor, minimizing damage to healthy tissues and enhancing patient recovery rates. These isotopic applications represent a fusion of nuclear physics and medicine where science meets compassion. The ongoing advancements in isotope production and radiopharmaceutical development continue to push the boundaries of what's possible in medical treatment and diagnosis. Radioactive isotopes, therefore, are not just substances, they are revolutionary tools in medical science, saving countless lives. The quest for clean energy has an unlikely ally: radioactive isotopes. In the search for sustainable energy solutions, nuclear power stands out, largely thanks to isotopes like uranium-235. This particular isotope plays a crucial role in nuclear reactors around the globe. But how does it work? Well, it all revolves around a process known as nuclear fission. Nuclear fission occurs when the nucleus of an atom, like uranium-235, is bombarded with a neutron. This collision causes the nucleus to become unstable and split into two smaller nuclei, releasing a significant amount of energy in the form of heat. This heat is then used to produce steam, which drives turbines to generate electricity. What makes uranium-235 so special is its ability to sustain a chain reaction. Once it splits, it releases more neutrons that go on to split other uranium nuclei. This chain reaction is controlled and maintained at a steady rate in nuclear reactors to produce a continuous and reliable power supply. The importance of nuclear fission in today's world cannot be overstated. It offers a potent source of energy that's not only powerful but also relatively clean compared to fossil fuels. Nuclear power plants do not emit carbon dioxide while generating electricity, making them a vital component in the battle against climate change. These isotopes are at the heart of nuclear energy, providing a substantial portion of the world's electricity. How do scientists track pollution or study climate change? Isotopes are their secret weapon. Imagine a world where we can trace the pathways of pollutants through ecosystems, or decipher the history of climate change. This isn't just a theoretical scenario, it's happening right now thanks to isotopes like carbon-14. These isotopes serve as tiny, yet powerful detectives in the vast and complex world of environmental science. Carbon-14, a naturally occurring radioactive isotope, is particularly instrumental in studying carbon cycles. When plants absorb carbon dioxide during photosynthesis, they also absorb a small amount of carbon-14. By measuring the ratios of carbon-14 to carbon-12 in plant tissues, scientists can determine the age of carbon in various parts of the ecosystem. This method is not only crucial for understanding how long carbon stays in the atmosphere, but also helps in assessing the effectiveness of natural carbon sinks like forests and oceans. Moreover, isotopes are invaluable in tracing the sources and destinations of pollutants. For example, isotopes can pinpoint whether the nitrogen in water bodies comes from agricultural runoff or industrial waste. This is essential for developing targeted strategies to combat pollution and restore ecological balance. Isotopes also play a significant role in paleoclimatology, the study of past climates. By analyzing isotopic ratios in ice cores, sediments, and tree rings, scientists can reconstruct past climate conditions, offering insights into how our planet's climate system has changed over millennia. Radioactive isotopes thus play a crucial role in environmental management and research, helping us protect and understand our planet. Today, we've explored just how intertwined our lives are with the fascinating world of radioactive isotopes. As we've seen, isotopes are more than just elements on the periodic table. They are dynamic tools that play critical roles across various sectors. In healthcare, isotopes are indispensable. They are used in diagnostic imaging like PET scans, which allow doctors to observe the metabolic process in the body in real time, providing insights that are crucial for diagnosing and treating diseases. Moreover, isotopes are vital in radiotherapy, targeting and destroying cancer cells with precision, thereby saving countless lives. In the realm of energy, radioactive isotopes are key components in nuclear power generation. They offer a substantial supply of energy, powering millions of homes and industries without the carbon emissions associated with traditional fossil fuels. This makes them an essential player in the shift towards sustainable energy solutions. Turning to environmental management, isotopes serve as silent guardians of our ecosystems. They track pollution, study wildlife migration, and even help in the assessment of climate change effects. By understanding isotopic patterns, scientists can make informed decisions that lead to better conservation strategies and a deeper understanding of our environmental impact. Indeed, the safe and informed use of radioactive isotopes is crucial. It requires stringent regulations and a deep understanding of their properties to harness their benefits while minimizing risks. From diagnosing diseases to powering cities and even tracking climate change, radioactive isotopes contribute profoundly to modern science and everyday life. Thanks for watching us share our videos, subscribe our YouTube channel, and press the bell icon, and stay curious for new uploads.